Hi all, today we are going to study the topic MMF for teeth and flux densities. So far in our previous video sessions, we have studied the calculation of MMF for air gap. The calculation of teeth MMF is not so easy. It is due to certain reasons which are given here. The very first reason is the shape of the teeth is either wedged one or tapered one, which is shown here. See, this is actually the shape of the teeth. Due to this tapered shape, the area presented to the path of flux is not constant. Since the areas at different sections of the teeth are not the same, definitely this gives different values of flux density over the whole length of the teeth. This is one major difficulty in the calculation of teeth MMF. Another major difficulty is due to the operation of teeth at the saturation region. As you all know, in the saturation region of the magnetic curve, for a small change in B, a very large change in H, that is magnetizing force, is required. Hence, the value of permeability, which is given by nu is equal to B by H, is very small. Since the permeability value is very small, then the reluctance becomes very large. As from the standard relation of reluctance, you very well know that reluctance is inversely proportional to the permeability. This causes a sufficient portion of flux to go through the slots. Hence, slots provide another parallel path for the flux. This presence of two parallel paths and the reluctance of one path which is depending upon the saturation of the other makes it more complex. Mainly three methods are employed for the calculation of MMF for teeth. Definitely the teeth is tapered in shape. The three methods are graphical method, 3-ordinate method and BT 1/3 method. In graphical method, first we have to calculate the flux density at various sections of the teeth. It is calculated by using the formula which is represented here, where phi is actually the flux per pole and nt is number of teeth under a pole and at is area of cross section of teeth at the desired section. Why we are saying it at the desired section? If you see here, the cross-sectional area over this section won't be the same as that of the cross-sectional area over this section. Hence, we are saying it as area of cross-section of tooth at the desired section. So, you will be able to see the flux densities at different sections which are calculated and plotted here. This portion is actually the root of the teeth. The length of teeth is same as that of the depth of the slot. So now we know the magnitude of flux densities at different sections of the tapered tooth. For each values of flux densities, you can easily calculate the magnetizing force, that is small at, from the corresponding BH curve or the magnetic curve. This curve indicates the variation of magnetizing force, which is represented by small at over the whole length of the teeth. The mean of this ordinate is indicated here, which is represented by at mean. This gives the equivalent value of h for whole of the teeth. The h is also said to be the MMF per meter. Hence, the total MMF for the teeth can be found out by multiplying the mean value of MMF per meter with the whole length of teeth. The length of teeth is same as that of depth of slot. So you can either multiply it with the length of teeth or you can multiply it with the depth of slot. Next method is 3-ordinate method. In this method, you will be able to find the MMF only if the teeth is having small taper. You will be able to see in this figure also, comparing with the previous case. In this case, we will be finding the magnetizing force at three equidistant points. One is shown here at the root and the other is somewhat near to the middle and the other is somewhat close to the tip. And from these values we will be able to calculate the mean value of mmf per meter by using the relation AT1 plus 4AT2 plus AT3 divided by 6. Just like in the previous case, once if the mean value is known, we will be able to find the complete mmf for teeth by multiplying it with the whole length of teeth or depth of slot. Next method is BT1 by 3 method. This method is also applicable for teeth with small taper. In this particular method, the magnetizing force or mmf per meter length obtained at a section which is about 1/3 of the tooth height from the narrow end is considered as the mean mmf per meter length, or it is considered as the mean magnetizing force, which is represented by AT mean. Hence the total mmf can be calculated just like in the previous cases. We have to just multiply it with the length of teeth or the depth of slot. Next we are going to study the most important topic of first module, that is the real and apparent flux density. Even in the recent supplementary exam which was conducted a few days back, problem on this particular topic has been asked. As we have mentioned in the difficulties in the calculation of mmf for teeth, there are two parallel paths for the flux over one slot pitch. There is in actual practice, the flux will flow through this slot as well as the flux will flow through this teeth. The real flux which is passing through this tooth portion alone will be definitely less than this total flux which is flowing through this slot pitch. Slot pitch is actually the center to center distance between these two slots. So if you are seeing the definition of a real flux density, it is actually the ratio of actual flux in tooth to the tooth area, and apparent flux density, it is actually the ratio of total flux in slot pitch by tooth area. Denominators of both these relations are one and the same. Since total flux in slot pitch is definitely greater than the actual flux in tooth, hence the value of apparent flux density is definitely greater than real flux density. The flux which is passing through this air portion of this slot is said to be phi A, and the flux which is passing only through this iron portion of the tooth, that is said to be phi I, and the complete flux over this slot pitch is said to be flux over slot pitch, and it is represented by phi S. Area of air path of the slot, see this flux lines which is going through this air portion in this slot, and its area is represented by A suffix A, and area of iron path of tooth is represented by A suffix I. So the apparent flux density can be found out from this relation, total flux over slot pitch divided by iron area over slot pitch. The whole flux over the slot pitch is represented by phi S, and the iron area is actually the tooth area which is indicated by phi I. This total flux over the slot pitch is actually the addition of phi I and phi A. So you can write B apparent as phi I plus phi A divided by AI. Phi I by AI is actually the ratio of actual flux in tooth divided by tooth area. So this can be represented by B real, or the real flux density. Then for the second term phi A divided by AI, you have to multiply and divide this term by AA. That is the area of air path of the slot. This phi A by AA can be indicated as BA, that is actually the flux density in the air, and the ratio AA divided by AI, that is the area of air path of slot divided by area of iron path of the tooth, can be represented as a ratio k. From the relation between B, nu and h, we can say that BA is equal to nu 0 h. Since it is flux density in air, we will be using nu 0 here, and instead of h we can write it as small at real. That is the representation. Small at is actually the representation of magnetizing force. And k is actually the ratio of area of air path of slot to the area of iron path of tooth. You can find out the area of air path of this slot by subtracting this whole slot pitch area, that is L into OS, with the area of this iron path of tooth. Then you will be getting the relation like this. We have already obtained the relation for BA. So in this relation, that is B apparent is equal to B real plus BA into K. Instead of BA, if you are making this substitution, the relation becomes like this. That is B apparent is equal to B real plus nu 0 ambient turned real into K. From this, the term B real can be written as B apparent minus nu 0 ambient turned real into K. Instead of K, you can substitute as Ks minus 1. So now you must know the relation between K and Ks, because in this slide I have written instead of K another term that is actually Ks minus 1. How we can substitute K with Ks minus 1? So first, in order to understand this, you must know what is actually Ks indicating. Ks is actually the ratio of total area over slot pitch by iron area over slot pitch, which is given by the equation L into OS divided by WT into Li. If you try to simplify the relation for K, the second term, numerator and denominator are same. So you will be getting the relation like this, L into OS divided by WT Li minus 1. This is actually Ks as I have shown here. So from this relation I can write K is equal to Ks minus 1. That is the substitution which is shown here. Instead of K, we have written Ks minus 1, where Ks is actually the ratio of total area over slot pitch divided by iron area over slot pitch. You must know this relation by heart, then only you will be able to solve the problems. Hopefully the concept of real and apparent flux density is clear for you now. Next we are going to solve the numerical problems related with real and apparent flux densities. In this problem you are asked to find the apparent flux density. Real flux density is given. Slot pitch, that is the value of OS is given. Slot width WS is given, and gross core length, it's very clearly represented as gross core length. It's not gross iron length. So this gross core length is actually capital L. If it was gross iron length, then it would have been L minus NdWd's value. Number of ventilating ducts, Nd is given, Wd is also given. Even the value of ampere turns real is also given. So all those things which are given is written here. You have to use this relation to find the apparent flux density. B real you know, ampere turn real also you know. So you just have to find the value of Ks. Ks is actually find out by using the relation L into OS divided by Li into Wt. Li can be calculated by using this relation, that is Ki into L minus Nd Wd. The value of K is given in the problem itself. Nd is given 4. Wd is also given. So you will be able to find the value of Li here. You can find the width of teeth from OS and WS by just simply subtracting them, which you have already studied in the reluctance session. So you will be able to find the width of tooth. Then making the substitutions, you will be able to calculate the value of Ks. Thereafter, you have to substitute the value of Ks here to get the magnitude of apparent flux density. In this relation, please don't get confused this Li with L. This Li indicates the net ion length, whereas this L indicates the gross core length. Please listen very carefully. This L is indicating the gross core length. It is not indicating the gross ion length. And this La is indicating the net ion length. Please be very careful with this. Let's see the second problem. In this problem also it is asked to find the apparent flux density. Wt is given. Gross core length. See, again gross core length is given. That is, the term L is given. Nd is given. Wd is also given. B real is given. Permeability of teeth corresponds to real flux density, that is nu real is also given, and the stacking factor is also given, that is Ki. Just like the previous case, you have to use the same relation. This value is given and B real's value is also given. You have to find the value of Ks. The value of Ks can be found out by using the relation L into Os divided by Li into Wt. Li can be found in the same manner just like how we have found in this previous problem. No doubt or confusions in that. The only problem is in this case the magnitude of slot pitch is not given. Even the width of slot is also not given. Only width of tooth is given. Then how can you calculate the value of slot pitch? In this sort of problems, you can consider the width of slot is same as that of width of tooth. That is, you have to assume the width of slot is same as that of the width of tooth, which is given as 10 mm. Then you can easily find the value of slot pitch by adding this two, and you have to make that substitution here. Then you have to proceed with the substitution in this relation. Then you will be able to get the apparent flux density. With this, we are completing today's portion. Thank you.